Okay, so hi everyone. So this is going to be the repeat stream of my DeepSpeed tutorial, which is a distributed systems library for making training larger models a lot easier. And so a lot of this comes down to like a whole bunch of bag of tricks that I thought this library does a really good job of covering and discussing like what they are, like how they work and why they're important. And so I'm just going to give you like all the background you'll need to pretty much understand all of these tricks and hopefully sort of train larger models yourself and go beyond like just like a single V100 or a single machine setup. Um, so yeah, so I guess like without further ado, we can just get started. Right. So really, like if you come here, like the first claim that they're making is like, look, we can train 10 times larger models, 10 times faster with minimal code change. And the idea behind the minimal code change is really, really important because ultimately you just want to be able to say, like, have your model definition, for example, in a high level framework like PyTorch or TensorFlow. So you'll have your init function, your forward function. And then when you say model.fit or model.train or whatever, these things should just work across multiple machines. And it's, as far as you're concerned, like this is totally like happening without your knowledge. But of course, making it debuggable and stuff is a lot easier. It's just that it's possible for you to start doing this stuff without spending too much time becoming an expert at distributed systems. So really, so there's a couple of important ideas here. The first one is that like, okay, well, they can train over larger models, making these things really memory efficient. So there's a couple of tricks related to another paper called Zero, which essentially gives you different ways of sharding models across multiple devices and across the CPU. And I'll talk about this stuff in a second. It also talks about scaling to extremely long sequence lengths. So when you think of something like transformers, well, for the most part, the default ones scale to up to 128 sequences. You can do more by, let's say, if you have like you want to work over a like sequence of length 256, you could concatenate two 128 representations and just use that as a representation for something that's a sequence length 256. However, you would much rather be able to just sort of do like a full like fully connected, like essentially like the issue with transformers, and I'll make this a bit more obvious, right? Like because you're essentially like for every given sequence, you're paying attention to all the other sequences. So let's say you're focusing on this word, that the number of that like an attention layer essentially scales like quadratically in the sequence length. So, if you remember stuff from big O notation, like as soon as you go for the quadratic stuff, generally everything is really slow. So this is a problem you want to avoid, right? And so one way to avoid it is to, let's say, split this into two and concatenate them. But another way is using sparsity techniques. And we'll be talking about those in a second, the different kinds of sparsity patterns. Right. So, and then they also talk a bunch about efficient communication patterns. And the reason this is important is that when you're dealing with distributed systems, often everything is slow because everything's underutilized. As in, you're just not sending data to the right devices efficiently enough and quickly enough. And so a lot of them just end up waiting. Or when you are transmitting data, you're just sending a lot of data. And so is there any way you can send less data so that the training can happen faster? Right, so they have a whole bunch of success stories here, like for example, using DeepSpeed with PyTorch Lightning, which is a high-level library on top of PyTorch, where they talk about stuff like CPU offloading, activation, checkpointing, and they have some benchmarks that you can see. Like it's really good. Basically, is what this is really trying to say. Um, they also talk about like here, like there's also like a Hugging Face blog where they talk about just like a single command line interface to, for example, be able to have floating point 16, which is basically on current NVIDIA GPUs, you can essentially increase the throughput of a device by about 4x by switching everything to floating point 16 with like close to zero code changes. In fact, like some of the newer NVIDIA compilers, I would suspect will just do this automatically for you. So this is DDP stands for distributed data parallel. So what data parallel is, and I have a whole YouTube tutorial just talking about the differences between data parallelism, model parallelism, and pipeline parallelism. I'll be covering the basics again today. But at a high level, data parallel is when you're running the same model across multiple devices. And then each of those sharded models will see a different subset of the data. And then they're each going to compute their own gradients, and then you aggregate the gradients somewhere centralized. So this is what this sharded means here. CPU offloading is sort of an interesting trick, and let me just talk about this briefly. So here, so generally, when you're thinking about like a GPU, for example, like let's say we're taking something like an A100. I think the on-device memory right now is like about like 50 gigs. So that means you can fit about like 50 gigs, like a layer that's about 50 gigs in size, before you start running out of memory. However, with a CPU, ultimately, this is just, you could just attach some RAM to this. And this could be, I don't know, like 100 terabytes of RAM for all you care. Like, I mean, realistically, let's say like a terabyte of RAM. I've never seen 100 terabytes of RAM. But the point is that here you have high, like you have like larger storage, but lower throughput. And here you have higher storage. Uh, yeah, sorry, you have lower storage and higher throughput, right? So then what's CPU offloading, right? So the idea behind CPU offloading is that if you have, like, imagine that your network consists of a bunch of layers, like let's say layer 1 to layer 2 to layer 3, all the way to layer n, right? And so what you discover is, like, let's say you do some sort of profiling, where you measure the total amount of time that's spent for every layer. Then you basically put the most time consuming layers on GPU and the rest on CPU. And so one reason why you may do this is because, like, I mean, GPUs are constantly in shortage mode right now. Like, everybody wants them. And so, like, if you're working with a limited GPU budget, then this is sort of a very reasonable thing to do. Another reasonable reason to do this is that, let's say, well, most of your, let's say you were to sort the layers by their size, and you just have like one layer that's just like absolutely gargantuan, like it's just like 100 terabyte layer or whatever for some reason, then it may make sense to actually put this thing on CPU. And yes, it's going to be slow, and yes, it's going to bottleneck everything else, but it just gives you a feasible way to even do that. Like, otherwise, you may not even be able to do this on GPU, except if you're doing intra-layer parallelism, which is a trick that I want to discuss briefly in a bit. All right, so here they're showing like a bunch of baselines, and it's like, pretty much these baselines saying like, look, everything's fast, and okay, look, it's just a config for the most part, as you can see. Uh, and so I guess without further ado, like, we can just sort of get to the meat of, I think, this video. So let's see here, configuration, what's new? Yeah, the features. So yeah, so this features overview is what I was referring to earlier. I think this is a great tutorial on distributed learning in general. It shows you just like at the high level, like what the ideas are, and how to work with them. So the first one, for example, is floating point 16, right? So like this is basically the latest versions of NVIDIA GPUs. Typically models are trained at floating point to 32 or 64, usually 32. But 16, you can get like 2 to 4x speedups, and pretty much for free. And the main thing you need to pay attention to is scaling the loss, because as you're transitioning the loss from floating point 32 to 16 and back, you could end up with discontinuities where you have like infinitely large losses. And so loss scaling is a trick to prevent this. But generally just use the defaults, and they'll be somewhat reasonable. And just as a high level, when we say we want this API to be, like zero code changes, often what we mean by that is, well, you could just say, well, this is the model I want to run. So that's client entry.py or whatever, or whatever other model, maybe the DS config, if you're doing a config driven thing. And then you would just give it a list of IPs. And that's pretty much how you would go about basically training on multiple devices as a user. Like, that doesn't tell you how it actually works under the hood. So just to talk, like, I just want to show you briefly as well. They talk about pipeline parallelism, and I just want to show you a picture that makes this really, really obvious. So this is from the Pipe Dream paper, which is another excellent distributed systems paper. I'd highly recommend it. I actually covered it on stream as well. So all these notes are from stream. So make sure to check out that video if this is interesting to you. And so as you can see here, like, this is sort of the vanilla scenario for model parallelism. Let me zoom in a bit. And so what are we looking at here? So on the y-axis here, we have a bunch of different machines. And then on the x-axis, we have time. So imagine that machine 1 has layer 1, machine 2 has layer 2, machine 3 has layer 3, and machine 4 has layer 4. So now you're doing forward propagation, right? So basically now this machine needs to wait for the result from this machine and this machine from the result of this machine. And so you end up with like all of these gray areas are basically times when no one is doing any work. Like the machines are just completely idle, and GPUs are expensive. And so you want to be able to utilize them highly. And this problem gets even worse, right? Because then when you're doing backprop, it's also the synchronous operation where you're just going to be waiting for the result from the layer that comes after you to be able to compute the gradient for your layer. And so it's just constantly waiting. So, you know, is there a way to avoid this, right? So for the most part, like when you introduce model parallelism, a lot of people think like, oh, so it just, you know, like it doesn't just increase linearly, right? Because you have this idleness issue. If anything, if you can avoid model parallelism, you always want to avoid it. Whereas data parallelism is something that you can pretty much get a lot of gains, like almost for free. So the way to solve this is with pipelining. And so what's pipelining? There's a visualization here. It makes it very obvious here, right? So imagine now, like let's say at every machine, let's say machine 1 gets the first batch of inputs, and immediately after computing the forward pass on that batch of inputs, you give it another batch immediately. So it doesn't wait for basically the next machine to tell it what to do. Now, it's still going to be waiting a bit during this forward pass. Like there's some idle time, but eventually you're going to end up in a state where when you're doing the backwards pass, you're constantly alternating between doing a backwards pass and a forward pass on the same machine, which makes it so that your machine almost becomes like pretty much fully utilized at this point. So now you're really taking advantage of the high memory throughput of your accelerator, as opposed to just having it be waiting around and not doing anything and just being just generally useless, right? So again, very simple trick that's very popular just in the computer architecture community. Like generally when you look at scheduling instructions on a CPU, like you don't just give it one instruction at a time, you give it a whole bunch of them at a time, such that whenever someone is waiting, it's possible, like because in a program, like a sequential program, there's going to be a lot of waiting around. So pipelining is one way to sort of amortize this communication cost and actually do something useful with your device. So moving on, model parallelism, we talked about as this idea of, well, like what if we want, like let's say you have a model with 4 layers, right? And then you put each of those layers on an individual machine. But what do you do if a single layer is so big that it can't fit on a single GPU? So one way is to offload it on a CPU, which we talked about this trick with CPU offloading. But another way is what's called intra-layer parallelism, which is an approach that I first saw mentioned by Megatron, which is a model, or again, a set of tricks for distributed systems proposed by NVIDIA. So let me just explain what Megatron is and why it's interesting. So I already skipped ahead to the 4th page of this paper, but what I want you to be paying attention to is this part right here, right? So we're doing what's called, so a gem is a generalized matrix multiplication, right? So what we're doing is we're multiplying a matrix X by A. And then after that, we're taking some nonlinearity on top of it. So this could be, here they're showing a Gelu, but it could be a Relu, or pretty much like anything else that you're already used to. Well, like, how can we potentially split these apart, right? Well, so one reasonable proposal is to say, well, like, let's say X is a square matrix. You just want to split it right in the middle, right? And so let me just maybe draw a picture to make this more obvious for you. So you just want to split it right in the middle, and then this is X1 and this is X2. And then you do the same thing with A1 and A2. And then you multiply X1 by A1 and you multiply X2 by A2. And the question is, like, can you just aggregate these two things together such that you get the Gelu of XA? Well, it turns out like not in the general case, right? Because you just need one counterexample where, you know, you could even try this out like on a simple collab, just to pick 2 X's and A's, and you'll see why this isn't true. And you'll notice like it makes it tricky for you to aggregate this stuff, at least in a sort of embarrassingly parallel way. And then the devices are still going to need to sort of talk to each other to figure out how to do the proper aggregation. So the main innovation that I saw that I found very fascinating in this paper is that instead of doing that, they essentially split A across its columns. So basically you keep X as is. And then instead you split A according to its columns such that you have A1 and A2. And then when you multiply XA1 and then XA2, if you take the GALU of this, right, and then the GALU of this, if you add them up, you get the GALU of of XA. So you can see here, this is a really simple and nice linear algebra trick, but it lets us actually come up with a good heuristic for how to shard large matrices on multiple devices. And so get the benefits of having a large layer with a large representational power, but at the same time not be as constrained by the on-device memory of a GPU. Right? So I think NVIDIA is generally heading down this trend where the on-device memory seems to be getting larger and larger every generation. Like I think mine is like 20 gigs or whatever, maybe 15 gigs. Actually, let's see. It's out of curiosity. Uh, Okay, yeah. So mine is 30 gigs, for example. So this is a 2080 Ti, but like I saw in the uh, in the later generations, like the A100s, they get 50 gigs, and I would suspect this just will continue becoming larger and larger over time. So again, very, very simple trick, but very powerful, and it gives you a good idea of how to do model parallelism at scale. Um, so the other thing to keep in mind now is that when you're like, yeah, so this just becomes a very important thing to consider, which is like just a general set of tricks that you'll see mentioned in another paper called Zero. So let's say you have let's say again let's take the 50 gigabyte GPU, right? And let's say you have your layers is about 49 gigs of size. Like this should fit, right? Well, not really, right? Because so 49 gigs this is the model weights. I'm just gonna make this a bit bigger. 49 gigabytes is the model weights. But you're still missing two things. So one, there's the activations, right? Which is, maybe like basically size of big O of number of outputs. So maybe let's say we're multiplying a matrix n by m. So pretty much m. And then here, like not really, well, m by, let's say then like m by, yeah. So m or m squared or whatever. One of the ones, like I need to double check that. But at least but they're not like massive. But like a very problematic issue is when you're actually doing back propagation. Well, a back prop is gonna have like, let's say you have all your weights like W1 to Wn for like, let's say for a given layer I, for example, right? So then for each of these weights, you also have a gradient update, right? So you have like sort of a delta W1 till like a delta Wn. Well, if this thing is 49 gigs, well, this thing is also 49 gigs. And so you may think that your model fits on device memory because you can do the forward prop well, but the backwards pass, you're going to end up with a problem where this thing overflows. And so the tricks with Zero are basically how can you offload the model weights, the model like how can you effectively shard model weights, model activations, and like model updates, such that you don't run out of memory. Yeah, so here, for example, like in activation partitioning, they talk about they're all gathered right before they are needed during the backwards propagation. By storing activations in a partition state, Zero and DeepSpeed can reduce the activation memory footprint proportional to the model parallel degree. So let's just read this again. In a replication of activations across all model parallel GPUs, stores these activations in a partition. Oh, I see. So basically, if you have intra-layer parallelism, this reduces the model updates proportionally by how quickly you've sharded it, and so the communication cost of like basically it becomes like beneficial for you to shard do model parallelism because then you can make it easier for you to also shard your activations. So another trick they talk about is constant buffer optimization, which is they enable high network and memory throughput while restricting memory usage to a constant size. So for memory bound operations like normalization and all reduced, so normalize like the performance depends on the size of the operand, simply fusing all operands into a single large operand. Okay, so operator fusing is huge. Like I think that the very simple scenario is like, well, let's say in your model, you have, for example, like a conv and then a relu, right? So these are two operations. So turns out, what if like your hardware provider actually gives you a highly optimized conv relu operation, And so basically, when you're compiling this model, like not you, like when your compiler is parsing this model, it's going to basically swap out all conv values by a conv value. And then your hardware manufacturer basically gives you a guarantee that this runs really fast. Right? So again, it's basically a way of using more advanced instruction sets that your hardware manufacturer would provide, and basically at the compiler level fuse your operators so that to make them amenable for the instruction set that your hardware manufacturer is providing. So another important thing is a contiguous memory optimization. And so the idea here is very simple, and you may have encountered this yourself already. If you've, I don't know, like if you play a lot of games and you download large games and stuff. So imagine that, you have about like a gig's worth of data. And you may think that like, okay, well, the gig is going to sort of occupy this. And then, you have 50 gigs and you're like, okay, well, now I want to allocate 40 gigs on top of this thing. Great. Well, it can fit. And now I have like 10 gigs left. Sorry, 9 gigs left. Right? Well, it turns out, like this is sort of in the case where the memory is all very contiguous. But let's take another scenario where maybe instead, you're like you were writing memory like in a very weird way, where you're just basically every 100 megs you're writing it sort of like in the middle of nothing. And so then actually, even though you're only using a gig, there's no way for you to actually fit 40 gigs without sharding it all over the place. So it makes sense to have an approach that comes back and defragments your memory and sort of turns this into something that looks more like this. So again, very simple and obvious trick. So again, and with offloading, it's like one of the things, remember, like we mentioned that CPUs you can basically attach as much RAM as you want to it, so it's going to be much slower. But it's like one way of being able to have the option of having insanely large models, at least, or maybe even in a temporary way, which is again like a very useful thing to keep in mind, where you're dealing with really large stuff. Like maybe you could have the CPU and then have the ops that can be really hyper optimized that fit in a reasonable size on a GPU. Although I will say probably like a better heuristic is just figure out how to make it small enough so that it can fit on multiple GPUs. And I think with intra-layer parallelism, there's no probably very strong reason to use CPU offloading. But it's good, I guess, also for stuff like embeddings. Like imagine you have a key value store. Well, like it's just absolutely massive, and all you're doing is indexing into various parts of that memory. Sharding that on the CPU is probably a good idea. So another thing to keep in mind is like smart gradient accumulation. So let's talk about this for a second. So generally, when you're doing distributed data parallel, imagine that you're going to have like a single data store that sort of looks like this, right? So this is your features. And then you're going to basically create a data loader, and then you're going to give various copies of this data to various machines. So let's say this is distributed data parallel 1, and then 2, and then 3, and then 4. Right? So each of these are going to compute their gradients, but eventually when you want to be able to actually have a model you can deploy, you would do what's called an all reduce operation, which is just a fancy way of saying like aggregate all of the weights or all of the gradient updates from everyone and put them in a single model that you can then use as your source of truth, or use that as a way to synchronize everyone else before you give them more data. So there's a whole bunch of ways of doing this. So this is one way of doing it. And you notice here that, well, this machine is going to be a bottleneck, right? Because it has to aggregate data from all of these guys. And instead, you could accumulate this in a sort of tree-like fashion, right? Where you can say, well, this node and this node can aggregate. So 1 and 2 can aggregate into like 1, 2. And then 3 and 4 can aggregate over 3, 4. And then this aggregates 1, 2, 3, 4. So this is one way, for example, of making the total data volume smaller. But there's other tricks. Like, for example, like one way is to say, well, like let's think about like something is being sent over the wire here. So let's say it looks like a bit like, essentially it's going to look like a vector, right? So it's going to be a vector W1 till Wn, right? And so the question is, well, instead of just sending a W1 till Wn, can we maybe send an H of W1 to Wn, such that this ends up looking like a W1 to WK where k is a lot smaller than n. So basically find a compressed representation of this thing. And so essentially the answer is yes, but not in the sort of naive way. And turns out the best way to do this is to basically send the difference between, like send the hash, basically send the hash and the reconstruction error. So basically, you're going to introduce some error natively because you're hashing this. You can measure this on the host where you're doing the hash before you send it. And this trick is called one-bit Adam, and it's essentially a way of sending compressed gradients for Adam in a smaller format. Right? And obviously, like there's other stuff like overlapping the communication. Like for example, like here, like you want to make sure that when, let's say here, that when this thing is actually doing a computation, that it's actually receiving all of the gradients at around the same time. That's why it's not just like waiting for a straggler. So again, just another thing to keep in mind. You just want to prevent waiting is really the general theme. Um, so another thing, I think it's pretty important to talk about is gradient checkpointing. And what gradient checkpointing is, I think I'm just going to show you this visualization that makes it really clear. But it's essentially a way of trading off the memory and speed of training deep neural networks. So this is essentially what backprop looks like. So with backprop, what you're doing is here, like let's say you're doing, let's start here. You're doing forward pass, forward pass, forward pass, forward pass. Great. Now you have the loss. So now when you're computing the backwards pass or the update, what you need, let's just make this visualization go over again. So you need what the layer before you says, and then you can sort of get rid of these activations like right here. Right? So this is really fast, but it uses up a lot of memory because notice that by the time we actually get to the final layer that we need to backprop, you have all of these weights that you need to store in memory, which again, in the case of these sort of GPT-3 like models, is just absolutely punishing. So what's another way of doing this? Another way of doing this is to just take the opposite approach and just say we're gonna use an idea called recomputation, where you basically just recompute the forward pass whenever you need it. So let's just go over an example. So let's say now, okay, you're just computing the forward pass, and notice you're always dropping the layer before. Now when you're computing the backwards pass, you're gonna need the forward pass for that node, and then you basically compute it. So this is like, see, like, so for example, here at this node, when you're actually here computing the backwards pass here, all you need is this and this, right? So you need this, and then to get this, you recompute it, and this, you get it. So as a good trade-off for this, like this is very poor computation-wise, but it's pretty good, memory-wise. Is this gradient checkpointing approach. So the gradient checkpointing approach is, it's very similar, but instead of keeping all of the forward pass activations, we're just going to keep it until one of the gradient checkpoints. So what does that look like? So you're going here. So now you've stored this, but now you're doing the forward pass. Well, you don't need this guy in the middle. But by the time you're doing your backwards pass, you can still leverage what the activations were at the checkpointed part. So again, I'd highly suggest that if this wasn't, if you didn't get it from this, I'll have the link in the description. So make sure just to stare at the picture. I think it makes the case very clear as to what the gradient checkpointing actually is. So other tricks, for example, are stuff like gradient clipping. So gradient clipping is pretty much a default thing that you would use in most models nowadays. Like if you have your own custom training loop and you look at the gradients and before you apply them, you clip them. And the reasoning is that you, like, if your gradient updates are too big, it's either going to zero out your model or make some nodes infinity. And so this is just a good way of ensuring the stability of a model. And you can always do this at a compiler level, right? So if this is a trick that everyone uses, then you as a user shouldn't necessarily have to write it. Your framework can help take care of this for you and add all the gradient clipping stuff to it. Obviously, some other stuff is mixed precision. So I already talked about mixed precision, but you can train in 16 bits and it increases throughput dramatically on GPUs. I talked a bit already about one-bit Atom, which is essentially a way of compressing the data that you're sending by also sending the loss. We talked about operator fusing, which is if you have optimized ops from your hardware provider, you can fuse ops that commonly come in a sequence into one and then do it in basically fewer instruction cycles. So this goes back to the whole like like should instruction sets be complicated and fast, or just have a simple thing that you can compile down to? So operator fusing is sort of more on the complex side of things, like more on the CISC or versus more on the CISC than the RISC side when it comes to computer architecture. Vectorized computing is obviously like a really big deal. So imagine that you're doing a ReLU on a vector. So like each element of that vector is going to be a real number, and then you do the ReLU of that function. Well, in this case, there's no sequential computation, right? If you were to just split that vector in two, then you can essentially run it on two machines. Or instead of on two machines, you can run it on multiple threads. And this is exactly what vectorized computations do. So whenever you have an operation that you're operating over a bunch of elements of a vector, SIMD instructions are very helpful, and Intel provides good facilities for them. And I think for the most part, most CPU providers also do. We talked already a lot about 15 floating point 16. LAMB is another optimizer where you can imagine. So this is, I think, layer adaptive something. I forget the name. Let's see what it was. Layer-wise adapt. So that, like, yeah. So LARS is layer-wise adaptive learning rates. So what's LAMB? Adaptive batch optimization. Okay, so works for batches. Yeah, sure. So, but the main idea really is this, that like usually when you pick a learning rate, you pick the same learning rate for all of the weights in your model. But you can imagine sort of intuitively that deeper, like the more shallow layers, if you change them, are going to have a very large impact on the output of the whole model. Whereas if you change just the final output, like it's still going to change it, but not as dramatically. There's not going to be sort of this like butterfly rippling effect. So a good trick is to essentially change the learning rate per layer. And you could also adapt it in a more algorithmic way where like if a layer doesn't change a lot, you can change you can change the learning rate for it sort of in an algorithmic way. So we talked about gradient checkpointing, parameter search with learning rate schedules are very important. So I want to talk about this, like learning rate range tests and one cycle rate schedules. So typically when we think about learning rates, I think the way they're usually taught is like, this is number of epochs, and then this is the learning rate. And then essentially it starts at some large value and you exponentially decay it to sort of fine tune the model over time. So this is how typically people think about learning rates. But the thing about deep neural, but this is really, I think the idea works best for convex models. So let's say your lost landscape looks somewhat like this. Well, this sort of makes sense because if you're around here, you don't want to take these large steps out. You want to just keep taking smaller and smaller steps. But the lost landscape of deep models, because they have like these nonlinearities and they're very complex, looks closer to like something like this. So it's not really obvious, like if you're here, like, well, what do you do, right? And so instead of like if you had a learning rate that just decays exponentially, where you're never going to get out of this local optimum. So instead, what one cycle range tests do is instead of having learning rates that look like a decaying exponential, you have them sort of take this like triangular upward shape. So what this does, and then to do it in a cycle. So it actually looks closer to this. And so the reasoning there is that like, well, you can slowly like decrease the learning rate so that you can find the local minima. But as soon as you get stuck in a local minima, it's actually better for you to take a large step out. So that way, potentially you could sort of get out of this local minima and maybe get to the true global minima, which is here. So range tests are then a heuristic to figure out like, well, how big can this whole thing be, right? Like, well, like how big can you make the learning rate before it gets really chaotic? And again, one intuitive heuristic is you can say, well, I'm going to pick a very large learning rate. And if the loss changes substantially from the past epoch, then I sort of went too far and I should pick a smaller value. So this is like what is intended by adaptively changing the rate. Data loaders are huge. So data loaders are basically when, like essentially, let's say like you have a disk, right? So you have a disk and you have your CPU and then you have RAM, right? And then you have PCIe, which is a communication protocol. And then you have your GPU, right? So typically here, like let's say if you have data, it's going to be stored in this, then you load it and then it's going to be like cached in RAM. And then when it's cached in RAM, the CPU needs to be responsible for sending data to the GPU over the wire. And so being able to efficiently stream data from the CPU to the GPU is the job of a data loader. And if you do this badly, what ends up happening is that your GPU ends up being underutilized. So it's basically constantly waiting for the CPU. And we talked about this. The main thing we want to avoid is avoiding having GPUs wait, because they're expensive, they're hard to find, and they'll produce results a lot faster if you saturate them. So again, they also have like some nice facilities for profiling, because again, you can imagine profiling a single model is already hard enough, but profiling a distributed model is much more challenging. So being able to count the flops happening on every machine, being able to figure out like the actual wall clock time of something is super important. Yeah, so it looks like finally the last thing they talk about is sparse attention. So remember, we talked here, where was it? Here. So you can see here, like essentially, imagine this is a token and needs to pay attention to all of the other tokens in that sequence, right? So is there a way we can sort of sparsify this representation, right? Well, so an attention layer is also just a matrix multiplication. So it's essentially going to look something like this, right? So you just have a matrix multiply. So this is a dense matrix. So how do we sparsify it? Well, there's a couple of tricks. Well, there's sort of random sparsity where you can say, well, for every one of these cells, flip a coin, and if it's heads, make the value 0. Sounds totally insane, but it's just like a good way to reduce the sparsity. Another way to do it is to basically have what's called fixed sparsity, where you pick a fixed pattern. Like for example, you're like, I'm gonna zero out every other node. So I'm gonna do this. And so as a result, you end up with a matrix that's like, if you use this heuristic, about half the size. And again, like these sort of sparsity mechanisms are very useful to just reduce the size of stuff, because then you can work with sparse layers. But there's a whole bunch of different ways of doing it. So here, for example, they have like what's called fixed attention, like fixed sparsity. But just to give you an example, if you were to click here, where is the documentation? Yeah, so for example, one way is to just say, well, like zero out the diagonal or whatever. And then different papers that deal with longer sequences typically have ways of sparsifying over longer sequences. So you can expect to see stuff like Big Bird or long former. So these are all tricks. So basically, just use whatever you think makes sense. So this is variable sparsity structure. You see how they sort of zero out like in this structure. There's like block sparsity. There's a whole bunch of, I could have a whole other video just about different sparsity mechanisms. Suffice to say, they're just all tricks to make what you're working with a bit smaller. So I think that's pretty much it. I think for our next video, I'm really interested in doing a video on lazy tensors and maybe another video on the DEX programming language, because I think it brings a lot of interesting ideas from the Haskell community and from stack-based programming, sorry, array-based programming like Futhark, to the deep learning community, and it's something I've been wanting to talk about for a while, so you should expect to see that soon. I've also had a lot of requests for doing more videos on ML ops, and so I am going to be reading the Andrew Birkhoff book on ML engineering, so doing another speed run of it. So if that's interesting, let me know. As always, if there's anything that you're interested in hearing about, please let me know in the comment section below. It makes it very motivating for me. Like I know that you're enjoying my content, that you want to see more of it, and it helps me guide it so that it's actually more interesting to you. So yeah, thank you so much, everyone. I really appreciate your time. And just remember, like, I mean, it's just, if you're thinking about distributed like model training, it's really about being aware of a whole bunch of tricks, whether it's using 16-bit precision, whether it's about using like operator fusing, gradient clipping, being able to offload memory or shard it, different ways to reduce the memory overhead, taking a single layer and sharding it over multiple devices by using a simple linear algebra trick. So again, a whole bunch of stuff, but hopefully this video gave you a good overview of all of them. So yeah, I'd highly suggest check out this library a bit more. Check out Megatron, check out Gshard. Like these are all good pieces of work to learn more about this. And I'll see you all very soon. Thank you so much.